All right, good morning, everyone. Let's get started with today's class. So the goal for today is to finish the spatial temporal variability exercise of yield that we started last class period. So if you don't have yet that project launched, please make sure you do that. Let me do that on my side as well. And we always want to launch the project, just a reminder about that, and then open the script if you need to. All right, so I believe that we stopped at the yield stability map for 2019. I think that's the point that we stopped. So on my side here, I am in the right project, right? So we see that on the top right. I have the script open, but I do not have any variables in my environment, and that's by design, right? So we don't want to keep our variables from one session to the next, because we can create those objects again if we have the script and the data. So if you already if you don't have your variables or your objects on your environment like I don't, you can come, and if you're looking at the outline, so we are on the, you can come to the SY20 chunk on the outline and just hit the run all above. That should work fine as long as you did not have any errors in your code from the previous class. Yeah.
How big of a deal is it if the objects do stay in the file? Do not, my environment was already had all of it in there whenever I opened.
Was it like, did you just open that project again and it was there, or was the project open? Okay, so yeah, so so Doug here is asking, what if you launch your project and the variables or the objects are already there? So
Hey, Dr. Bob,
yes.
can you share the screen for us?
Oh, yes. Sorry
Thank
about
you. Are you good?
our screen. Well, yeah, I think I may be sharing the wrong screen, maybe. Because it says,
Yeah, we just.
let me try again. So I think I was sharing, but maybe for some reason.
Sounds great.
All right, yes, sorry about that. I think I was sharing, but maybe I selected the wrong window. Okay, so Doug is asking, like, if he launched the project and the variables are already there when you open it. So that behavior is something that I discourage, mostly because sometimes, like, you may come here and you play with, I don't know, maybe the wrangling part of things. So maybe you decide to today want to change something here, that you change and you run it, and then this object is created here. But then maybe tomorrow you come back and you add something else here, but you forget to run. So the actual object that is in your environment is the one from yesterday, which does not reflect what you wish you would reflect from today. So that discrepancy there can cause some issues. And I think, it's not like this is not that it causes issues every time, but it has the potential of causing issues. So just to avoid having that potential issue with any script, any project, I encourage that we do not save our environment from from having the project open today, closing it, and then opening it again, even today or tomorrow or another time, and having your variables come up automatically, or your objects. So for us to inhibit that, let's see, where do we go? I believe it was tools and then global options. So tools, global options. I think it's right here. So on the general item here on the left menu, on the basic tab, it has this workspace. If you have, so I would assume probably if you're seeing your variables carry through, you probably have this checked. So you want to uncheck that. So you don't want to have this checked. And then you can change this. If it's not if, if it's saying save workspace to our data on exit, if it's not never, make sure you change it to never. So that's what is going to, so you don't want to have this checked, and this should be never. And then you can come on the bottom and click apply and okay. And that should be reflected. All right, so I guess coming back to, if you go to the SY20 chunk, which you can find here on the outline on the side by toggling the outline button on and off. If you come to that and you click on this button here, this button is for run all chunks above. So it's basically gonna get us back to the exact place that we were last time. So you can click on that button. You can see the green progress bar going on here. If it doesn't go through the end, it's probably because you have some lingering error in one or more chunks above. So if you have an error, it stops on that error and it doesn't keep running until where you are. In which case I would propose that you just come all the way to the beginning and run chunk by chunk. That way you're going to be able to see where the error is and perhaps delete that or fix the error so you can keep going. All right, so I'm assuming everyone was able to run all above and get to the point of SY20. So here on SY20, we're basically just going to apply the same wrangling steps that we were doing for SY17 and SY19. In fact, if you just want to go back to your SY19 chunk, so I just went back to the SY19 chunk, and I'm just going to copy starting at the, I mean, we can even start at the data frame level. So yield 19, and then copy everything all the way to the end of that select, because the steps are going to be the exact same ones. So once you copy from SY19, let's go back down to the SY20. We give the assignment symbol and we paste what we copied from above. Now there's a couple things here that we're going to have to change, as we have already done that for the SY19 when we copy from the 17. The first one is the data coming in. So now it needs to be the yield IC20, right? This is the interpolated yield for 2020. And then we also need to change here on the select. So we're creating this, SY, well, let's just walk through again on this code since we're starting fresh today. So yield IC 17, 19, and 20, they all have this, this look, right? So you have the IP yield pound per acre, meaning that's the interpolated yield in pounds per acre, and then the geometry. Our goal here is to standardize the yield of that specific year and standardizing by the median of that field. So the next step that we do here is we calculate the median using the mutate function. We give the column name median yield pound per acre, and we do that by getting the median value of the column IP yield pound per acre. So we're getting the median of all values in this column. And again, because we're using mutate, even though that is one value, right? So it's going to be the same value for everything, but that value is going to be repeated all the way down for all rows of this data set. It's going to be the same value for the median, because again, it's the median for the whole field. And then the next step, we do the SY, which is just dividing our interpolated yield by the median and then multiplying by 100 to get this in a percentage. And then finally, we're just selecting that SY column and on the fly renaming it to SY19 and also keeping the geometry. So if you run it all and you print it, you should see this now, where our values of the SY19 are going to be in percentage. And because we are normalizing by the median, if we look at all the values under this column, they should be centered around 100, but they should go above 100 and below 100 as well, because we're normalizing by the median. Again, if we were normalizing, for example, by the maximum instead, then our percent values would always be at most 100, but lower than that, because you're dividing by the maximum value of that field. So nothing can be higher than the maximum, right? All right, so I left you, I believe, all the code here to make the map as well for SY20. So if you want to go ahead and run that. And you can print it. So I got an error here, SY20 not found.
The 19 and the
Oh, yeah.
last code, right?
Yes, thanks. I'm glad that you're all paying attention here. So I forgot to rename this to SY20. Right, so make sure that you do that change on your side since we copied this from SY19 and just needed to edit it. So if you make that change, now this code should work. All right, so just as a reminder, we are creating a ggplot and then assigning that to an object, right? And then so if I want to see this plot, I have to ask for this object to be printed, and I can do that just by running the object name. So this is how it looks like for 2020. All right, so we've done the standardized yield where we standardize by the median for each one of the 3 years. So in our case, all these 3 years were cotton. However, if let's say they would have been maybe soybeans, peanuts, corn, cotton, any combination of that, or even different crops, this would not have mattered at this stage because we have already standardized by the median, which yes, the median is dependent on the crop, but once you standardize it by it, they all fall in the same range of relative values that are going to be centered at 100 and then be also lower and higher than that for different parts of the field. So the next step here, I also left you. So I want to create a plot where I combine all these 3 maps side by side so we can compare them and be easier to look at all 3 together. To do that, we're going to use this the package called Patchwork. If you ever need to do combinations of different plots, then you want it to look at very professional and sharp for a publication, do look into this package in more detail. They have a very good vignette online with many examples of how you can combine different plots. It's really, really worth it. So we're going to use this package Patchwork. And once we load Patchwork, and I just want to make this distinction here so you don't get confused. If I do not load Patchwork and I try to use this plus here, so all these objects, SY17, 19, and 20 map, they're all ggplot objects, right? So they're the ggplot maps we created and assigned to these objects. If I do not load Patchwork and I try to use this plus, it's going to give me an error because it's looking that you have a ggplot and then you're trying to bring another ggplot after that. It doesn't work. However, because we load Patchwork and it sees that there are 2, or in this case, 3 ggplot objects that I'm trying to connect with a plus, this plus here is actually coming from Patchwork, even though it looks like ggplot style. So when we do that, if you just run that piece of code, this is what it's doing, right? So it is taking each one of the 3 maps, and then I have this extra, well, let's say if I just inhibit this, so I just run the 3 maps without that plot layout. This is what it does. So remember that if you go back to the code of each one of the ggplots, we allowed the legend to be on the 2017 code, but we said theme inside the theme function, we said legend position equals none for 2019 and 2020, which removes the legend, right? So if I just run like this, we get the legend for 2017, but it's like in between those 2 maps. So by using that plot layout collect guides, and guides here, they mean legends, that basically takes that legend of one plot and puts at the end of all 3 plots, collected at the end. And again, why did we keep only legend for 2017 and not for 2019 and 2020? Because the legend is the same, right? Now that it's standardized, it does not make sense for me to have 3 legends that have exactly the same color, same range, same breaks. It's just, we don't need that, right? So that's why we did it. All right, and then I left you the code here for you to export this as well using ggsave. So something kind of interesting to notice, and perhaps, you know, if we just take a quick moment here, I will ask like to the whole class, and then I'll ask for a couple people to provide their inputs here. So where are we seeing the consistently lower than the median values in this plot, in this field? Where is that happening across all 3 years? Can you say that? Say that again, sorry.
Erosion area.
Yes, so Sunday's saying the eroded areas. Yes, right, so if you remember from the satellite imagery, these fingers here are like eroded areas of this field, right? Also on this boundary here, on the outer boundary, which is probably also related to water movement and how this field is changing. So something that I think is really interesting as well is if you look at this particular area, in 2019, it had some of the highest relative yields. But if you compare that with 2017, you had some lower than the median, and 2020 was a little bit more mixed as well, right? So this is getting to this notion that there is spatial. So within the year, we have spatial variability, but across years, we have this temporal variability of yield that is being driven by different factors, right? And our goal here is try to understand what's driving that, and if that is something we can manage, or is something that we just have to, I guess, live with it and maybe not necessarily manage for better yield, but just understand that's a low yielding area that we cannot do much about. All right, so on the next chunk here, I left you the code as well, just for us to look at this. So we're using the summary function on the standardized yield of each one of the years. So I'm gonna run line by line here so I can see each one of them separately. So for the standardized yield of 2017, we see that is ranging from, in my case, in yours may be a little bit different again because of the boundary and the grid, but ranging from 24 to 156%. Again, this is based on the median. So if something is 100% here, it is exactly like the median. And also to remind you, on statistical distributions, the mean and or the median would be the values that are most commonly appearing in this data. So that's why also the mean and the median of this median value or of this standardized values are centered around 100. All right, so if we look
Perfect.
at, yes,
In the map where you have the spatial stability, the 3 maps 2017 through 20, I noticed that you have in the legend you have from the highest yield to 140, and I have 160, and I think that's what you had in the code, and I don't know if that was a difference.
yeah, that's a good point. So what we did here, well, let me see. So for the map of 2020, I did the breaks, I guess, going from 0 to 120 at intervals of 20. Let me see what I did for the other two. So the same for 19 and the same for 17. So what is happening is we are allowing it to have breaks that go from 0 to 180, but probably because it's looking at our data and it's just not, so what would be, so what it doesn't tell us here is the next level, even though it's not, it doesn't have the number there, but it would be one. So the top here would be 160, the bottom here would be 20. So if our data is still within those limits, right? So we're looking here, we're still very close to those limits, at least on the upper limit. If we had at least one point that was like 180, that would force this legend to show the 160, and then the 180 would be, I guess, implied as the next break. Like right now, the 160 is implied. Does that make sense?
Yeah. So if I have 160 mean, I have the higher data, right? When I select the boundary.
Yeah, so
Yeah,
if the legend here is showing 160, because we allow the legend to go all the way to 180. In my case, it's not going all the way because I don't have values that get close to 180. in your sides, it may be a little bit different because of the boundary that we all did differently and therefore the grid, right? So it could be a little bit different and that's fine. And that's something you can actually inspect right here. So if we come here and run these summaries that we're doing now, and you see that like your maximum for at least one of these layers is like more than 160, then I would expect for you to see the 160 break and then have one more level after that, that would be implied at 180. So maybe let's check that Rolando, what you're telling me is that your legend is showing 160 number here. Is that what you're saying?
Yes, sir. And
So-
by running the summary on 17, 19, and 20th, like on 20, I have the values are 179, 167.9, and 160.8.
Okay, so that's the reason why. Oh, it's interesting here because so and that's really, it's a really good point as well, because you know what, that's a great point, because last time I taught this, we all had the same boundary, so we're all on the same page. So let me actually do a fix here, because on my side, if you see here, these values are the ones I got last year when I ran this, and they're not exactly the same. So now, I'm getting the minimum of 24, which is close, the maximum of 156, so a little bit different, still close, but a little bit different. But on the other years, I'm getting 6 and 178, so my maximum on 2019 is higher this year for some reason. Potentially because of one of the filters that may have applied a different buffer perhaps, and that changed things. And the SY20 the same, so I'm going a little bit lower. So really on my side, on 2019, I should see this scale being higher. However, I'm basing my legend on the 2017 data. One thing we can do, well, I guess there are two things we could do. So one of them would be to actually keep the legend only for the year that has the maximum value. So that would be 2019. Another thing would be to go back and work on the scale fill of the 2017, because we allow it to change the breaks. But I did not specify the limits of that scale. I did not say I want the minimum to be 0, I want the maximum to be, I don't know, 180 or something like that. So we can go back and see. So what I would say is take a look at these three, right? Especially your minimum and maximum, and take note, just like I did here, of what was your minimum and maximum for each one of the years. So mine was 2017 was 24 minimum and 156 maximum. 2019 was 6.4 and 178. And 2020 was 33.7 and 154. So again, yours, as you already aware, are not going to be the same as mine, and that's because of the boundary and the implications that has on the grid, which has implications on the interpolation. So if you look at your values, maybe we should have this range here being to not just the breaks, but the limits of this scale to be 0 and 180 as well, at least on my case. If you have values that are greater than 180, then you can change that to whatever value you have. So the way that I would address this is if we go back to the first map that we made, so the 2017. So here we're seeing the breaks, but this does not force for these breaks to be present if the data is not within that range, or if the data is less than the breaks are given. It has an argument that if we give a comma here, that's called limits. I think, let's try that we give two values using the C function. The first one is the minimum value that I want to have. So let's say 0. And the second one is the maximum that I want to have. In my case, I'm going to say 180. In your case, if you had a maximum in any one of those years that was more than 180, then use that number. So I ran that. I did not get any errors, so I think it worked. So now if we printed, yeah. So now we're really forcing it to start at 0 and to end at 180, as you can see here. even though 2017 does not have data past 160, right? But because we're using the same scale for all three maps, we need to standardize by doing that. The thing is, we're also gonna have to do the same, add this limits here to our scale field gradient 2 to the other two maps. So I'm just gonna copy this. So make sure that you run this, right? So you update your object. Again, you know, why we want to not have variables coming in, because imagine that you just add this text, but you forget to actually run it. So your object in there, SY17 map, is the one that you did previously. You know, so we want to make sure that we have the most up-to-date objects in our environment. So I just added the limits here on the 2017 and ran it. So that change would appear in the map. I'm coming to the SY19 map. So this next one on the scale field gradient 2, also adding a comma and giving the limits from 0 to 180. If we run this, we're not going to see a legend because we're inhibiting that from appearing. But now the values here, the intensity of the color has changed to represent that, even if the legend is not showing. And then we go to the next one. So the SY20 map, and do the same thing, go to scale field gradient 2, add that comma, paste that limits equals to C0 and 180. And run it, and then we can just print it. All right, so after doing all that, if you rerun this last piece of code here after the patchwork, now we all should have this exact same legend, and maybe potential a little bit different values inside of it, just again because of that, because of the grid, of the difference in the boundary. Something I want to point out here, and this is something that you're going to come across a lot of times in your research or whenever you use data, same data for the same field across different years, or maybe same data for different fields, even within the same year. So what we're doing here is we look at all three maps, all three data sets, and we said, let me find the lowest value across all three and the maximum value across all three. And let me force an equally, like an equal color scale for all three, which is what we did here, right? So if you look at that, what happens then is, perhaps on the 2020 is a good example. On the 2020, I did not see any of the cells being super dark purple or super dark green. They're kind of like in between, right? I do see the most intense purples on 2019 right here. I do see some of the most intense greens also on 2019 right here. And that's because 2019 had both the highest values, but also the lowest values across all three data sets. And I guess what we're talking about here is more from a design, like a map design / interpretation approach. By combining the minimum and maximum across all three maps and making one common legend, we are basically dimming perhaps the intensity of some of the maps that are not near to the minimums or are not near to the maximums of all three, which is a trade-off. Sometimes, perhaps what you would like to do is actually allow this legend here to change from year to year in a way that the legend would take a minimum maximum value of the color scale to be just within that year. If we did that, then you would see very dark purples and very dark greens in all maps, because now each map have their own legend, right? In this case here, I decided to combine all the values and have one common overall color legend, so we could compare the intensity of, you know, how is standardized yield changing over time. But this is just, you know, maybe something for you to think about, because whenever, again, imagine that the same thing happens a lot when we work with satellite or with imagery overall. So imagine that we had, I don't know, 30 satellite images for this field in a growing season. If I let each one of those images have their own individual color scale, they're all gonna have greens and purples. However, if I have one common color scale across all the 20, 30 images for the growing season, the ones early on are only gonna have purple. And then as the crop grows and this number increases, they're gonna become more green. And as the crop senesces, they're gonna become purple again, right? So this trade-off between having a common legend across all maps or having a legend or a scale, color scale for each individual map is something to think about. Awesome. Thanks, Rolando, for pointing that out. And I guess we diverge a little bit, but I think it's a good conversation to have. All right, so let's get into our spatial temporal stability analysis. So you all read the paper, you all submitted your assignments. So for us, so right now we're doing more the spatial aspect of that within each one of the years. Now for us to do the temporal, we have to actually combine all these three data sets into one and then apply the rules that you read on the paper, right? Or I guess then calculate the metrics first and then apply the rules based on the metrics. All right, so I guess, I have a question here of how can we merge these pieces of information to create a spatial temporal classification? So if you think about it, we have three different objects right now, where each one of them is for a different year. Each one of them has the standardized yield. How can we combine them? What do you think we will have to do next year? So if we don't even think much about like in programming terms, but more just, from the workflow that we would have to do just using words, we basically have to bring all these three together in the same object first, where we have a column for standardized yield for 17, another column for 19, another one for 20, all in the same data frame. And then we can start doing some of the calculations that we need for the temporal stability aspects. Also, if you remember from the paper that you read, what they were doing is, so once we bring all these three together, we need to calculate for each pixel. So perhaps pixel is not the best word because it's not a raster, but for each polygon here that would represent a cell in all this field, we need to calculate the mean standardized yield across all 3 years. And then we need to calculate the coefficient of variation of the mean across 3 years. So now we're not talking, let me just take one step back here. When we did the standardization here, we got the median for the whole field within that year, and then use that to standardize. Now that they're all standardized on the same scale, we bring them together, and we do that is basically, a lot of times in geospatial data, we think about bringing data or bringing layers together. We think of stacking them, which is what we're doing, is just that we do that just by merging those columns into the same object. And then we're going to look at where each row of our data sets. So, if we look at SY17, each row here is one little polygon inside of that map. So now for each one of those little polygons, those little cells, we're going to calculate the mean across all 3 years and the coefficient of variation of those 3 years. And then, as you saw in the paper, we're going to use those metrics to apply rules and determine stability, temporal stability on these data sets. Does that, I know, I'm just telling you things, we're not seeing that yet, but does that kind of make sense as far as what we're going to do next? So the immediate next step here is to join these three data sets into one. That's what we have to do next. If you come to this chunk here, I want to do that and assign it to this object called SY all for standardized yield all. We're going to start off with SY17. Give it a pipe. So in the past, whenever we wanted to merge or join two data sets, we needed to have a common column between them, right? I guess you remember that because we've done that a couple times, I guess. In this case here, because these are spatial objects, these are SF geospatial vector objects, we do not really need to rely on a column. We could if we wanted, but we can actually rely on their spatial position. Because all these three data sets were created based on the same grid, those grid cells would line up. All of them should line up across different years. So we're going to make use of that property to combine them based on the spatial location of those cells and not necessarily on a common column. So to do that, there is a function called st_join, which again is to do joins, but based on spatial objects. So the first argument we give here is the second data set that we want to join. So we're starting with SY17. I want to now bring SY19. So inside of st_join, the first argument is going to be the SY19. I want to change a couple of arguments here. So it has an argument called join that the default, I believe, is st intersection. I want to change this to be st_equals. If you, and just a heads up here, it's going to try to give you the actual function with the parentheses there. I think if I remember well from when I tried this the first time, if you leave those parentheses of the st_equals, I think it does not work. So I just want you to just delete that and just leave the word st_equals without the parentheses. And then it has a last argument we're going to change, which is called left. So if we want to do a left join, I want to say true. I think that the default is false. So what's happening here is it's going to look into those two objects, SY17 and 19, and look for where they have an equal, well, what is the word I'm looking for here? So the equal, so that the cells are exactly in the same space across two different layers. So that's the join we're doing. That's called st_equals. And then left join, it means that we are taking the SY17 and then which is on the left side here, and bringing SY19, which comes from the right side, I guess. So that's why it's called left. It's a left join because we're merging 19 on 17 and not the opposite, not 17 on 19. That's why the left equals true does for us. So if you run that and you print it for us to inspect, this is what should have happened. Now we have the SY17 data that you had already on that SY17 object. You have the geometry that is coming from SY17, but then you also have this other column SY19, which is coming from the SY19 object that we just did the join. Now, it is really important here to check your number of rows. They should be the same. So, the number of rows of my SYAll, which is the join data set, has 4,046 rows because those are the number of polygons that I have in this map. The little polygons that represents the cells. If I check here SY17 by itself, so before doing the merge, the join, SY17 has that same number of rows. And if I print SY19, also has the same number of rows. So I would expect that after joining, the object SYAll remains having the same number of rows. That's what it should happen. All right, so the next thing here for us to do is to repeat the same step and bring in the SY20, right? So you can just go ahead and copy right after or right before the pipe here. Copy that, and you can just paste it right after the closing parentheses of that join. And the only thing we're going to change is the data set name. So now is SY_20, right? So we're starting with SY17. We're doing a spatial merge of SY19 and doing again with SY20. If you run all this, your SYAll should still have the same number of rows, but now it should have one more column, which is the SY20 standardized yield for 2020. Save this here. Okay, so we did join all of them. Now we have the right data in the right place to calculate the mean and the coefficient of variation for each one of these rows, right? So again, each row here is a cell or a polygon in each one of these maps. They all have the same spatial overlap. They're all in the same position across all 3 years. So now, if we look here, what I do want to have is do the mean. So this first row here, I want the mean and the CV of these 3 observations. So the mean between 91.1, 89.3, 98.5, and have a column that has the mean of those 3. And then another column that has the coefficient of variation of those 3, right? So remember that when we were doing group by and summarize, we were creating groups, but we were summarizing the column values within the group. Now we're actually going row wise, not column wise. So we're gonna see a different function to get, in this case, a statistical summary, mean and coefficient of variation for the row instead of for the column. So if you come back here to your SY all objects, add a pipe there, hit return. For us to set the structure to tell that we want to calculate something at the level of the row, there is a function called rowwise. So we're going to say that if we just run that by itself, it doesn't do anything. Right? I mean, still same number of rows. We just get this new option here saying rowwise that is just specifying that whatever happens next is going to be rowwise. So let's add a pipe, and now let's ask to calculate a new column where we're gonna get the mean of those 3 columns. So what we do here is we're gonna use mutate, as you may have been thinking already. And I wanna call this new column mean underscore pixel. So because I want the mean, we're gonna use the mean function, right? So let's call the mean function. And here I need to tell the mean function what columns I want the mean of on a row-wise pattern. So here we need to use the C function to tell it that I want SY17, comma, SY19, comma, SY20. So these here are the name of the columns, right? Are these names here that were just given it to ask for the mean. All right, if we run that, and then you print the object to see what happened. Now we have this column here called mean pixel that has the mean of all of those 3 values of that row, right? So we have a different mean value for each one of these 4,046 rows in this data set that are all related to each one of those polygons in the map. Okay, so now we have the mean of each one of them. The next thing for us to be able to categorize these temporal stability is the coefficient of variation. If you remember, R does not have a function that does coefficient of variation directly for us. However, it does have one that does standard deviation, and the coefficient of variation is just a function of the standard deviation and the mean. So we already have a mean. We need to calculate standard deviation first so we can get to coefficient of variation. Let's add a pipe. Let's do a mutate. I want to call this next one SD underscore pixel to calculate the standard deviation. So R has a function that's called SD for standard deviation, and then we just give again the same 3 columns using the C function. So I just copied the C function and the 3 columns from the line above and paste it below. So if we run that, we're going to get our standard deviation. And now we can calculate our CV, which is the metric that we need to do the temporal stability. So we add a pipe. Let's do a mutate. I want to call this next one CV underscore pixel. And that the formula for coefficient of variation, if you want to open and close parentheses here, it's going to be the standard deviation of the pixel. So SD underscore pixel divided by the mean. So mean underscore pixel and then outside of the parentheses times 100. So this is how it should look like on your side. Okay, if we go ahead and run this, and we just print it, now we have the mean and the coefficient of variation. This is the percentage, right? So this would be like 5%, 5%, 4%, and so on of each one of those pixels. All right, so I think,
Just give a second to catch up.
yeah, you mean on the code here?
Yes.
Okay. Okay, so as Kumar is finishing up here, I just want to keep going and just explaining what we're going to be doing next. So now, if you remember from the paper, the mean and the coefficient of variation are what we need to create the spatial temporal stability classes, right? That's going to be our step after here. The thing is, before we get to that, I do want to create some plots and some maps for us to visualize what the mean and the CV look like in this field. So that, again, I guess one of the drawbacks of using a programming language is you don't get that immediate interactivity with the map as you would on ArcGIS or another point-and-click software. So we have to, create those maps ourselves. Can I keep moving here?
Yes, sure.
All right. Okay, so first thing, I just want to get here a summary of I think what we're doing first is just a summary of the CV. Just understand how much is that variability changing. So here we see that the CV is going from, very little, almost like this is less than 0.1%. all the way to 75%, meaning that there are some pixels here that have a very low CV, meaning they're very stable. So they're either, in being very stable, it means that they're either always low yielding or always high yielding, or always medium yielding could be as well. However, we have some with very high coefficient of variation. This means that these pixels are probably changing behavior from year to year. And that's what we want to know is where are these pixels? And how can we understand what is driving that variability from year to year? All right, so let's actually look at the distribution using a density plot. So we're gonna call ggplot. The data is that sy_all that we created above. Let's call the AES at this level. For a density plot, so is that one that kind of looks like a normal distribution? For that, we only say what goes on the x-axis. In this case, is the variable of interest. I want to explore the CV_pixel. And then we get outside of that AES, outside of ggplot, add a plus, and do geom_density. That's going to give us a density. And again, this is perhaps one of the only ggplots that we do not give the y-axis because the geom density calculates the density for us, which is based on the data. So that's why we don't give the y-axis in this case. So this is that distribution of the CV. We can see that it probably the mean or median in this case, the median CV is probably around, I don't know, just under between 5 and 10%, it looks like. But then we have this long tail here, meaning that we have some observations that are way out here. At least that's what shows on my side. On your side, again, it may be a little bit different, but the overall pattern should still be there. If I actually want to know where my observations are, there is another geom that we can add here. So let's add a plus, and it's called geom_rug. So what geom_rug does is it puts here on the x-axis the actual position of each one of the data points. So plus geom_rug, and we can look at the position. So we see here that really most of the data is probably within 40% coefficient of variation, and we have a handful of data points that are larger than that, and really just one that's sitting all the way at 70%. All right, so we explored the statistical distribution. Now I want to explore the spatial distribution of this using maps here in ggplot and assigning that to this object called sy all mean. So let's start coding here. We're gonna call it ggplot. We're gonna leave it empty at that level, just add a plus. So my goal here is to plot the sy all object and show you the standardized mean column. What function do we need here? Any guesses? Renalisa, what do you think?
Oh, you're gonna define your plot.
Yeah, so my goal is to create a map similar to this, but now but to show the mean across all years, right? Which we have as a column. And the object that we have that is the sy all, which is the one that we combine all 3 years. So what geom do we need here to show that? No guesses? Doug, what do you think? So let's take a look at perhaps if we just get the class of S. So we know that the data is in sy all, right? And that I want to plot this column here. So sy all is an SF object. So what do you think? What geom do we need to show that? geom_sf, right? So geom_sf, we're gonna say data equals to sy all. I want to give it a comma break line just to make it easier to read. And inside the AES, I want to say that I want the fill to be according to the mean underscore pixel, right? Because I want each one of those polygons to be colored according to the mean. That's my goal here of this map. And outside of AES, I just want to give it a comma and say color equals NA. So we inhibit the outline of those polygons to make it a little bit cleaner to look at the plot. If we just run this and we print it, this is what we see, right? So now we're looking at the mean of those pixels across all 3 years. I do want to make a couple quick changes here. So first, I want to change the scale of the color, or in this case, of the fill. So scale, let's do scale underscore fill underscore Verities B. So B is for binned data. So even though mean pixel is a continuous variable, but we're creating bins out of that to make it a little bit easier to visualize. And then I want to change. So if we run this, just want to show you what that does. This is what we get. I do want to change the option. So if you remember, the Verities scale has options that go from A to H, I think. The default, I believe, is D. I want to change the option here inside of that to be equals to C. And I think this has to be uppercase. So if we print that, this is what it's going to look like. And then finally, I want to set the breaks here to be specific. So let me ask you all this. From the paper that you read and the answers you gave me, what were the breaks that they were using to determine the difference between low, medium, and high yielding? That was based on the mean. What mean percent breaks were they creating the categories in that paper? 80 and 120, right? So I do want to have that in this map so we can visually assess how these would relate to those thresholds. So it has an argument called breaks. We're going to say breaks, and then we give the C function and we say 80 and then 120. So this is how that looks like when it comes to those two breaks. So very interestingly, I guess, well, let me ask you all what, maybe someone from Tifton, what do you see here? Like, how would you, if you give me a quick interpretation of this plot, can someone in Tifton help me out, at least to begin with, to start with that interpretation? Oh, yeah.
We can see in the map, we do not have like much high yields. We have like medium.
Yes, so the medium class, the medium yield class is the majority here, right? And then. Yes, go ahead.
Got a few high yield spots and then lower yield down the low side of the field that's eroded, but it's fairly consistent.
Yes, yes. So we see some, like, there's not too many, like, high yield points on this field, right? Where what would be considered above 120% of the median across all 3 years, right? So there's not a lot of those. The majority is the medium, category, and then the low yielding means across all 3 years are again at or close to those areas that we know are eroded parts of the field. Awesome. I guess one last thing I want to do here on this plot is just add a plus and do a theme map, as we've been doing, just to create a more clean looking map for us. So I just added a theme map at the end and ran that, so it would show up. All right, so let's go ahead and do the same thing, but for the coefficient of variation, and look into that. So here, let me see, I think we can actually, let's do this. Let's just copy this code that we did here. So starting on the ggplot, all the way through theme map, let's just copy that and paste that here on the CV. And we need to adapt this code now to show the CV, right? And we're gonna do that. Well, what would be the first thing that we have to change here to make it show the CV instead of the mean? Where would you make that change on this code?
In AES,
On the field, right? So
Yeah.
if we just print again, that I just selected SYL and ran it, so it would print below. So that column is called CV_pixel, right? So that's what we want to show here. And also I want to propose, so what was the threshold of the coefficient of variation that the paper proposed to be, values under it are stable, values above it are unstable?
30.
30, right? So let's just have one break here, and that would be 30. So we have this threshold and can visualize that in this field as well. All right, so this is what we're seeing here, where most of the field is actually would be considered, at least on my side here, you're probably seeing at something similar on your side, where most of the field would be considered stable. And then there are some parts of this field that are considered unstable. So the unstable parts are those that have a high CV across the different years, which could mean that in 1 year, it's very high yielding. In another year, it may be low yielding, right? So it's flipping its behavior depending on the year. All right, so if you come to the next chunk here, I just want to combine both of those maps again and just export that using ggSave. So we have this PNG map saved on in our files. And just to inspect, if I come here and output, I should see both of those objects. So the combined spatial stability one, right, that we did standardizing to the median for each one of the years separately. And then the spatial temporal stability one, which is combining all 3 years and getting the mean for each one of the cells and also the CV for each one of the cells.
Home's not combined.
Yours was not?
We give it, we give us a code,
So this part of the code or?
yes.
Yeah, so this part of the code, I think you already had, so I would assume this would not be where the issue is. So what I would, so if you ran this, SY, this line of code here, and you don't get both maps to print below,
Just give me the, that's why, just give it to me. And then I'll-
oh, okay, so if you run this chunk like all together, well, in my case, I guess it is showing the maps below. But sometimes if you run the whole chunk and you have a GG save as the last thing, it may export it but not print it for you. So what I would do is if you go to your files tab on your output folder and inspect that object. So that is the SY temp stability.png. If you open that, you should see the map there.
It's showing both of them now. The first time it only showed the CV. But I didn't run the whole chunk, so I think that.
Okay, so now that's working now? Okay. All right, good deal. Well, before we get into the actual classification, any questions or thoughts about this?
Can I see the code for the standardized mean CV map, please, Professor?
This one here?
Yeah. Great.
Yeah, so this code here, we copied and pasted from the above, and then we just added it. So we changed two things. One was the variable that we're assigning to the fill, and then the break.
Okay.
All right, so let me see here. I think we can get through. This is probably a good point for us to take a quick break if you all need, maybe like 5 minutes, and then we can go through the classification and then learning of what's happening with that classification. So let's take because our class today goes to 11:10. So this is the halfway through. If you want to take a 5-minute break, feel free to do that. And then after you're back, we're going to continue.
I wanted to ask you one thing.
Hmm?
It is with respect to the exam that we will have in March. It is because I want to plan accordingly in the spring break. Will it be online or it will be offline? And do I have to be on a specific location? Something, what will be the format of it?
Yes, so the exam and actually we need to talk about the date itself and where it stands as of now. I think that date is probably going to be there because we're making progress to the point of concluding all the exercises that should come before the midterm. So right now that date's going to be what it is. But so the way it's going to be is wherever you are on your campus, that's where the exam is going to be. So those in Athens should come to in-person class here. Those in Griffin should go to the in-person class there. And those in Tifton, the same thing. So it should be the in-person location. And there's going to be a person that will proctor the exam in your locations. Since I will be in Athens, somebody else is going to help me to proctor the exams in the other campuses.
What is that?
So let's take a look here. On the schedule, just to make sure I tell you the right one.
Is that gonna be like the on paper or?
No, it's gonna be in class. So right now is for Friday, March 15th. So in about a couple weeks. Yeah, so this is gonna be basically related to what we've been doing until now, right? So we can talk in more detail about this when others are in class as well. But it's basically, it's gonna be on paper, so we're not gonna have to do any coding. There will be coding questions though, especially of things that we've been doing a lot and that I would expect for you to know already. So there's, it's not gonna be any tricky questions, but some questions related to things we've been doing a lot. So, for example, how would you read in a vector file, like a shape file? Well, you know what, maybe I shouldn't be telling you all this right now, because I know some people took a break and I want to be respectful of that. Let's pin this for a moment and get back to this conversation after the break, so everyone can hear it. Yeah, let's do that. All right, so our 5 minutes are done, so let's continue here. And when we get to the end of this exercise, we're going to take a moment to talk about the midterm exam. Okay, so let's just again remember of what we did up until this point. We brought the 3 interpolated, clean process EO maps for the different years. For each one of those years separately, we extract the median and then standardize all the yield values according to that median, in a way that now we don't have yield data anymore in pounds per acre. We actually have percent, right? So a percent or a proportion, well, yeah, I guess we did a percent. So a percent of the median, that's the unit that we're working with now. So it's ranging from 0 to 180%, depending on the year. So now after we standardize, we have that standardized yield for all 3 years. We combine them by extracting the mean of each one of the pixels across years, and also the coefficient of variation, right? Which is what we're looking at now. Now, the next step is to actually implement these, I guess, use these columns here and implement the rules of the paper that we read to create the spatial temporal stability classes. Okay, so just a quick refresher here. The rules that we're going to implement here, the first one is going to be based on the CV, right? So we did our map with a threshold of 30 because that was the number proposed by the paper. So if we come here and we do The first filter being that CV. So everything that has a CV greater than 30% is gonna fall into this class that we're gonna call unstable, right? So anything that has a high CV is unstable regardless of their mean yield or their mean standardized yield. Everything else that has a CV less than 30% then is gonna fall into the next part of that classification, right? So if something is less than 30% CV and has a mean standardized yield greater than 120%, we're gonna call that high stable. Again, if it is a CV less than 30% and a mean standardized yield between 80 and 120%, then it's medium stable. And if it is less than 30% CV and a mean standardized yield less than 80% is called low stable. All right, so I think it's always a good exercise for us to create the understanding of what we want to do with words and just thinking, normally as a human would, and then implement and try to then connect what do I need in coding, in programming to implement that, right? So that's what we did here. We put on paper, or I guess on the scripts, in words, what we want to do. And now I want to ask your help for us to develop the code to implement these. So if you come here on the next chunk. So the object that we need to begin with is the SYAll, because that is the one that has the mean and the CV at the pixel level, right? So we started off with SYAll. I do want to print it below just so we check that that's correct. So this has the mean pixel and the CV pixel columns, which we're going to need to use here. Okay, so let's develop this together now. What would be the next step for us to create these rules? Maybe we can begin with by what function do we need here? Ujwal, what do you think? Okay, so what can you tell me more about why do you think we need a filter?
To define the range, like the CV and the standardized yield.
Okay, so let me just give you this feedback. If we use filter, then we're gonna be only filtering certain rows, but the others are gonna be left out, like outside of the other data set. So maybe filter is not exactly what we need. So if you think about it, maybe let's imagine this way. I want to create a new column here that we'll give it a name. I think I'm calling ST class, where under this column here, it's going to look at the mean pixel and the CV pixel that we're going to give the rules on it. And this new column is going to have a value. So it's still going to have a value for each one of the rows in this data set, but that can be one of unstable, medium high, or medium unstable, medium stable. My gosh, take a step back. Unstable, high stable, medium stable, low stable, right? So each one of these cells are going to have one of these 4 values. So for us to create a new column for all of the cells, mutate, right? So let's go ahead and add a mutate here. I want to propose that we call this column ST class for spatial temporal class. All right. What should come next? Did somebody say something?
Concatenation.
Can you say that again?
Concatenation to
Okay.
include the separate classes.
So it's not directly concatenate here because we're giving conditions, right? So we have these 4 conditions here that we need to give. What have we been when we give conditions? Yes.
If we start with if.
Okay, we could go that route, but I'm trying to make you all think of something we've used already in the past, and I think Renalisa said something here. Case when, right? Yeah, so Renalisa said case when. So Kumar, just to follow up on what you're saying. To implement a condition type of logic, if could be used as well. I don't know if you recall, but when we went through one of the exercises, we used case when, which is an easier way of having multiple conditions. If we use if, we could do that, but it would be less readable, I guess, because we have to nest multiple ifs inside each other, and
Yeah.
that makes the code less readable. But it is the logic of an if,
Okay.
so you were in the right track. Okay, so let's start with case when. So case when we use when we have more than two or more than one condition that we want to specify. I want to break code here just so we go to the next row. And all right, so let's print SYAll just so we inspect again the name of the columns. This is what we have. And the first rule that I want to implement is the first one on this list. So I want to implement this rule here. If a pixel has a CV more than 30%, then it is classified as unstable. Can someone else that hasn't helped yet help me here with how would you write this first condition, knowing the condition, knowing the threshold, knowing the column names we have in this data set? Neva, what do you think? Okay, so Neva said CV underscore pixel greater than 30, and then what? Well, so I guess we still have not finished this condition, right? So do you remember how this works? So we give the condition and then we say tilde, right? So tilde is to say if this condition is true, then, so that then is what this tilde means, right? Then we say what is the value that we want to give it. So we want to give it unstable, right? Yes, so that's it. Thanks, Neva. All right, so we're saying here that inside this case when is where we give the conditions. We're saying if CV pixel is greater than 30, then the value I want to assign to the column ST class is unstable. That's what we're saying with this code here. All right, so first condition, done. Now, the next condition is going to be this. So if the CV is below 30% and the mean standardized yield is greater than 120, then we want to classify as high stable. Let me ask someone from Tifton, perhaps.
I think we're gonna do the same way, but if CV is less than 30,
Okay, so Benicio is saying CV pixel less than 30. What comes after that?
then high stable.
Okay, so we can do that, but there's something here. So there's something missing here, right?
You need to add like a plus. And then the yield greater than 120, or I don't remember how you combine the two values.
That's right. Was that, who was that?
Dalton,
Dalton, awesome, Dalton. That's the idea, right? So the way that we give two conditions is we add an and with this symbol. So the next condition would be mean underscore pixel greater than 120. Right? So this would be, again, so if CV is more than 30, does not matter the mean pixel. It's unstable, period. If is less than 30% CV, then we get into that and break that down further between high, medium, and low stable. All right, so we gave two conditions. We still have two more to go. I guess this next one here is probably the most involved of all four. So let's try to do that. So the next condition is, let's see, if the CV is less than 30 and the mean standardized yield is between 80 and 120, then it is classified medium stable. So let's implement that. I'm gonna help whoever is the next person here by already saying CV pixel less than 30% and I'll stop here and I'll ask for someone else to tell me how should we implement the in between 80 and 20? How would you do that? What do you think, Doug?
Would you have, at the hand symbol, mean pixel is greater than 80?
Yes, okay.
And mean pixel is less than 120?
Yes, you're corrected. So what Doug's saying here, just for those online to follow along. So if the CV pixel is less than 30 and the mean pixel is greater than 80, so we establish the lower boundary of that and have to at another end, mean pixel is less than 120, right? So here we are starting with the CV pixel and then defining the lower and upper boundary of the condition of the mean pixel. Then this is equals to medium stable. We add a comma, and now we're gonna give the last condition, which is not as complex. So the last one, I'll help the next person here. It starts with CV pixel less than 30, right? So remember that only the first condition was CV pixel more than 30. All the other three were based on CV being less than 30. So how can we tell now that I want the mean pixel less than 80? Sendes, what do you think?
Here for them 20 and this thing.
Okay, so could you repeat that again?
And in pixel greater than 20
Mean pixel greater than 30?
and in pixel less than 80.
Okay, so interesting. So let me ask you this, what if a mean pixel is like 20? Then it's not gonna fall into any of the conditions, right? So I guess what I'm asking you is what is your train of thought for giving a lower boundary here? So if we look at the condition, right, coming from the paper, if it's the CV is less than 30 and the mean standardized yield is less than 80, then that's stable. Right, so here we should have mean pixel, if CV less than 30 and mean pixel less than 80%, right? Then the pixel is classified as low stable. All right, so if we run this, well, I got an error. Well, I misspelled pixel in one of my code. Let me go back right there. So you should have been able to run this appropriately. Now, if we go all the way to the right here, now each pixel has a class that is one of the 4 classes that we created. Right, so this ST class column is what that represents.
So we didn't change the decimal points, but say if we did have different decimal points than the whole number, would that cause an issue with no equal to, it have left out 30?
That's a great question.
80?
It could have. And if for some reason we have any given, so what Doug was asking here is our CV and mean pixels were not integers, right? They had like many decimal points. What if they were integers? So instead of 4.8 it would be 5. Would the conditions we gave without giving an equal in any of the conditions, just less than and more than, could have that caused a problem? And the answer is yes. So the way that, and that's a great point, because I don't think we are gonna have this issue here, but we can see how we would address that. So on these Boolean operators, Boolean operators are things like less than, more than, equal, different, and so on. Right now, we're just giving like, more than or less than. We're not giving more than or equal to. We're not giving that equal to right here, but we could. So what we could do, let's say, we can just give that equal sign. I believe it has to be, let me see here to make sure I'm telling you correctly. Because I know that whenever you're saying equal to, greater than, or equal to, less than, there's a right place of the equal, and I don't remember now if it's before or after the less than and greater than. I think it's after. So this would work, but I think this would not work. So if we do this, so yeah, maybe let's go ahead and change this to incorporate the equal to as well. So in this case here, if CV pixel is greater than or equals to 30, then it's unstable. Because the other side of that condition is less than 30, then we do not give the equal sign on the less than 30, right? So we just give the equal sign in one of the breakpoints of that condition. So I'm giving here greater than or equal to 30, it's unstable, and then less than 30, which does not include 30, is unstable. Now let's do that same for the mean pixel. So if I want to say greater than and equals to 120, just give the equals there. Now, if we come back to the mean pixel as well, I can give the equal on the 80, but I need to leave the equal out or not include the equal on the 120, right? Because remember that every time you have the same threshold, you want to have the equal in one of those conditions, but not in the other. Because something cannot be equal, because if something's exactly equal to 20 and I have the equal here as well, then where does it fall, right? Should it go in high stable or medium stable? So we just want to have the equal in one time of that given threshold. So we're giving that right here. Same thing for the 80. I just given the equal on the 80 here of the medium stable. So I'm not going to be adding the equal to the less than 80 on the low stable. So this is how we would address that. All right. So next thing here is let's make a plot, right? So let's see how these are changing in space. So we start off with the ggplot. We add a plus. The object is called SYAllClass, which is still an SF object. So we need a geomsf. We're going to say data equals to SY_all_class. Still inside geomsf, let's give it a comma and call it a yes. So we're going to say, I want to color the pixels according to the class that we just created, right? So if I print below here SYAllClass, just so we can inspect, that column is called STClass. So I want the fill to be equals to STClass. And then I get outside of the yes, and I want to say color equals NA, so we do not have the outline on those polygons. If we just go ahead and run this, this is what we get now. So before we talk too much more about this, I just want to make some quick edits here. I hope you're already anticipating what I'm going to say because we've been doing this a lot. I first want to change the color scale. So let's add a plus. I want to change to scale underscore fill underscore Virides. And now because, so this column STClass is a character column. So it's non-numerical. Because it is character, it is also, you can also interpret it as a discrete column, right? So I have discrete values in it. So I need the Virides underscore D, that D stands for discrete. And again, I want to change the option inside Virides to be equals to uppercase C. It's just a different color scale. And lastly, I want to clean this up by calling the theme map. So we have this cleaner theme for us to look into. I want to show the code just for a second here in case you need to catch up, and then we're going to talk about what we're seeing in this plot. All right, so let's talk about this plot here. So notice that now each one of the cells has only one of those classes that were based on the CV and also on the mean pixel across all 3 years of data. You know, I guess for right now, actually, let me just so we can see better, because the theme map is bringing the legend to overlap. So for now, just so we see, I just want to have it like this, so we don't have the legend overlapping. All right, so let me ask you, I have a couple questions here that I want to ask you all to think about, and then we'll discuss more. So just by eyeballing it, what seems to be the major stability class and what seems to be the minor one? What do you think, Rolando?
Can you repeat the question, Professor?
Yeah, so just eyeballing on this map here, what do you think is the stability class that has the most points or the most polygons as part of that class? So what is the major class here and what is the minor class?
I said that would be the low stable.
So the low stable is which one?
No, I'm sorry. The medium stable is the orange.
So the medium stable is the majority, right?
Mhm.
That's pretty easy to eyeball that. What do
And
you
then
think is
the
minor
least one, it will be the unstable.
Yeah. Yeah, I think the minor one's gonna be either the unstable or maybe the blue one, which is the high stable. Right? That also looks like has just not too many points. So probably one of the two. Yeah. Awesome. So very interestingly here is that we do not have a lot of high stables, which I guess, you know, it would be nice if we did, because that means that this grower has parts of the field that are consistently high yielding regardless of the year. So they have most medium stable in this case, which is, not bad. It could be, it could be worse, right? It could be all unstable. So imagine that if you have a lot of yellow in this map, a lot of unstable, meaning that you really don't know how your field's going to do this year, right? Like it can be a very good year. And this is just a heads up, this is an irrigated field. So instability on yield can come from weather, and that's probably a relationship between weather and soil properties as well. But when we're talking about the same field over time, weather is going to be a main driver, and especially rainfall. But this field here is irrigated. So it's really interesting that, if we were to have a lot of unstable cells here, then it means that there's something else that is changing from one year to the next that is causing that instability. And if you think about it, unstable classes are probably the hardest ones to deal with because you don't know what's going to happen. If you come you look at this map here and you see there, wherever you have, let's say the high stables, you can say, well, these parts of the field, I know I can use more inputs, so I can use higher seeding rates. I can apply higher rates of fertilizer. I can, protect more with fungicide, pesticides in general. That is areas of the fields that will respond consistently. On the other side, on the low yield cells, are parts of low yield and stable low yield. You know that maybe you can cut down some inputs because it is not going to give you the return. It's not giving you that yield year in, year out. But the unstable is really unknown, because if it's based on weather, with the assumption that weather is the main driving force to make it unstable, it means that, you don't really know if this year is going to be a good weather or maybe a bad weather, and even what does that mean? Does that mean total precipitation? Does it mean timely precipitation? Does it mean volumes of it, number of cloudy days? Is it temperature, highs, lows? There's a lot of weather variables that can be causing this instability that is really tough to decide how to treat. So these are things that are interesting to think about as we look at this type of data. All right, so the next thing that I want to do here is to actually calculate the proportion of cells within each one of these classes.
Can I ask you a few questions in between?
Yes.
These are simple coding questions, and I just want you to explain me why in the above chunk we have used color is equal to NA after aesthetics. I'm unable to understand that. Just,
You mean right here?
yeah, right there.
Okay, so Kumar is asking, why are we setting color to NA? So something I want to encourage, I guess everyone is, this is coding. So it's really easy for you to try things on your own. I do encourage you to do that. You cannot break it, right? If you try something, I mean, I guess you can get errors if you try something, but then you can always go back to the previous states. So Kumar, to answer your question, why don't we do this? Before I do on my side, why don't you and maybe other students that are interested in the question do that on your side? So let's say what you would have to do is so inhibit this comma here and then inhibit the color and then run that and see what would happen if we do not say color NA. So Kumar, what happened there?
I am unable to find a difference. I mean, there are grids more visible, I guess.
Yeah, so in this case here, did somebody say something? No. So in this case here, because we're changing the fill, so the fill is the color inside of it, and the color argument is refers to the color outside of it. So the outline color of that. I mean, I guess there's nothing wrong with leaving that outline color here. It's just that it adds a little bit of extra noise that is really not relevant to us, right? I mean, I really don't care about seeing that black color there. I'm more interested in seeing the cell actually. So maybe like on your side, if maybe if you have the one where we inhibited the color NA, so look at yours, that should look like mine right now. And now I'm gonna do the color NA for us to inspect it. Right, so I think you would probably agree with me that it's like when we remove the outline, which is really not useful, I guess in this case, we can see more clearly the color of the fill. Right, so it's just to remove that noise that is not really giving us any information with the color outline. You just let the fill come through more.
Okay.
All right, and I just want to now let my theme map go through as well. So we have a cleaner version of it. All right, so the next thing that we want to do, that I want to propose that we do is we actually calculate the proportion of each one of these classes within this field. Okay, so to do that, the object that we're going to use is again the same one that we created above. So that's the SY all class. If I just bring that below so you can see what that is again the all number of rows we've had with the classification ST class. Okay, so let me tell you, I think I'm looking at the code that I have developed, but because we all have different boundaries, I think I'm gonna edit that on the fly a little bit here. So the first thing that I want to do is, so for me to be able to tell X% of the medium class or X% of cells were classified as medium stable, X% was classified as unstable, and so on for all the classes, I need to know the total number of rows first, because so it's just a calculation of, it's going to be two steps here. Where one, we need to know what the total number of rows is, which is going to be different for each one of us. And then we need to know how many cells fell within each one of the classes, and then we divide those two numbers, right? That's going to be the proportion. So let's do the first thing here is use a pipe, use the mutate function, and I want to calculate the total number of rows. I want to call that uppercase N. And that is basically going to be the number of rows of this data set. So I think we need to say n row and then use a dot notation for that to properly work. So if you run this, now you have this new column that has the number four, in my case, 4046 running down all the rows. Because again, I use a mutate. Right, so in my case, 4046, in your case, it could be a different number because of the boundary. All right, so the next thing now is gonna be to calculate the number of cells within each one of those classes. I hope that you're thinking that we need a group by here. Every time you want a summary over levels of a column. So I want the summary, in this case, the total number of observations within the different levels of ST class, we need a group by. So adding a pipe, let's do a group by. What is, so again, let me tell you what I'm looking for. I want the number of observations within each one of the ST classes. What column should go inside of the group by? ST class, right? So ST class should come here. Then now we add a pipe. And there is a convenient function. I don't know if we have used this in the past, but there's a convenient function here that's called tally. So tally does exactly that. It gives you the number of observations within the groups of a given column. So if you run this code, you're gonna get this new column called lowercase n, which is the number of cells within each one of the classes. And we got that by doing a group by ST class and asking for the tally of that. One thing that I want you to notice is now the uppercase n that we created is not here anymore. And if now we do the same mutate and row, is gonna return 4. If we do that same mutate uppercase n after the tally, is gonna return 4. So of course, like we could simply say, now that we know the total number of rows, we could just use that number that we're seeing in that we know there's, like in my case, 4046. But this raises a different perhaps challenge that you're gonna find whenever you use group by. So what group by is doing is doing that group by and giving you what you're asking, but it only keeps the group by variable and then whatever you're asking it after that. It removes all the other columns. And this is a larger, I guess, challenge, because not just on this exercise, but in any exercise, because sometimes you want to keep more of those columns and not just lose them. The way that you would keep more columns is you can just come here on the group by and give that column on the group by as well. So if you think about it, the uppercase n only has one value. So it's not really going to group by n because n is just one value. It doesn't make sense. But it's going to carry over that n for us, that uppercase n for us. So we can actually use it to then calculate the proportion. All right, so at this point here, we can just add a pipe. And I want to create a column that is going to have the proportion, right? So to create a new column, we do mutate. I want to call this prop for proportion. So this is basically going to be, if you open and close parentheses, just to give a formula there, is basically going to be lowercase n divided by uppercase n, get outside of the parentheses and do it times 100. This is going to be our proportion. So if you run that now, and you have to scroll to the right here to, at least in my case, I have to see. So we can notice that 84% of the cells were, let me see if I can show all columns together so we don't have to be going back and forth. So let me do a quick trick here. So we'll just select. Gonna use a pipe and do a dplyr select ST class and prop, so we can see them side by side. So we see that 84% was medium stable, as we were guessing already from our visual inspection of that map. And then really close here, the high stable and the unstable both have just under 3% of the cells are classified as both of those. And then about 10% is low stable on this field. So this is how we would calculate that proportion. So really, being a medium stable is interesting because there are certain inputs that are based on yield level, right? So for example, nitrogen, we should apply more nitrogen where you expect a higher yield potential. If it's a crop that does require nitrogen, right? So a non-leguminous crop like corn, cotton, and others. So in this case here, we could come, I would expect that the medium stable average yield to be low or to be lower than the high stable, but higher than the low stable, right? Because again, these are based on yield. We got to these classes based on yield. So if we were to go back to the actual yield levels, I would expect for the medium stable yields to be medium within the range of this field. And then we can use that information to say, well, on the medium stable classes or cells, I will apply a given nitrogen rate that is based on the yield potential of that medium stable class. And that rate could be different for between the medium stable and the other classes, right? So you could decide to apply less nitrogen to the low stable, and a little bit more nitrogen to the high stable. And then really the unstable is the joker in this case here, because we really, we don't know how it's going to behave this upcoming year. But anyways. All right, so lastly, let's export this layer here to file. So how do we export an SF object? There we go. Write SF, right? So read, yeah, so read is to bring in, write is to export. So write SF, the object name again is sy_all_class. We give it a comma. We're going to give it the path. So open and close quotation marks. We get outside of the code folder. We go inside the output folder, or in this case here, I guess I'm exporting to the data folder. So maybe let's do that, since it is a data we're going to be using. And I was calling this sy_all.geojson. Then we give it a comma, and remember that every time we're doing write SF specifically, we want to change the delete_dsn to be equals to true. If we don't change this, it is equal to false by default. And if you run the same code twice, it will append. So it will create more rows each time we run. So we do not want that to happen. We just want it to overwrite. So delete dsn equals true. All right, so a quick summary here. On this exercise, we, again, imported all three interpolated clean yield data. We standardized each one of those years based on the median of that year. So this is, I just want to highlight here. One thing that you could decide to do is to combine all the yield data points at that level in one data set for all 3 years, and calculate the median of all 3 years together. So it's not the median for each year, is the median of all 3 years together. That is one approach that we could have done. We would have gotten a different median value that would be one median for all years. I don't think that's the goal here, but I just want to bring that up because you may see that in different, like in papers or different methods. So we want to calculate the median of that year specifically, because when we standardize by that number, we're basically removing the effect of the year, right? Because now, okay, so this is, I think it's an interesting point for us to explore a little bit further. So if this year was a very good year for crop yield, like I had high yield. So let's say my cotton, I was getting, I don't know, my field was averaging, I don't know, 2,000 pounds of cotton blend per acre. And then next year, it's a bad year, it's a drought, I don't know, it's just a year that is not very good for yield. And I have half of that at that yield level, the same crop, same field, just 2 different years. So one year, the average is 2,000 pounds. The other year, the average is 1,000 pounds of yield. Same crop, right? It's the effect of the year. If I go on each one of those years and get the median separately and standardize by that first, now everything is gonna be centered around 100. However, if I go and get the median of both years together, which in this case may be like, I don't know, let's say the median would be more like 1,500 pounds of wind per acre, and then I divide both years by that one number, now most of the points on the bad year are gonna be low yielding. Most of the points on the high yield is good, on the good year is gonna be high yielding. So it kind of defeats the purpose, right? So that's why we get the median for each one of the years and divide all those data points by that median itself, and not a combined overall median across all years. All right, so after doing that, extracting the median for each one of the years and standardizing the yield value of that year by that year medians, then now we have the standardized yield that is centered at 100% and goes lower and higher than that. If we were using the maximum, for example, to standardize, the maximum value as a percentage would be 100% and everything would be lower than that. After doing that standardization, we joined all of them, calculated the pixel-based mean coefficient of variation, and then use that to apply the rules we read on the paper to come up with the 3 classes. And then finally, we exported that spatial temporal stability layer so we can use later. Okay, a couple of things I want to tell here about this before we talk a little bit about the midterm. So the more yield data you have, the better, right? Because then you're going to be able to more consistently see what is the effect of different years on crop yield for that field. So the more, the better. In our case, we have 3, which is probably the minimum I would recommend that we do have when we're trying to do spatial temporal stability analysis. If you have only 2 years, well, I guess it's better than having just 1 year. But even if you have 2 years, you know, if you have if one of those years is a really good year for yield, the other one is a really bad one, then you may be making decisions that are not really representative of the average weather of that you see on that field. So really 3 perhaps is the best, or the minimum, but then the more you have, the better. So if any field that you're working with, if you can get access to yield data across multiple years, that's probably going to give you a better understanding of yield stability of that field when you do this type of analysis. All right, I guess any questions about this exercise before we talk about the midterm? All right, I don't hear anything, so let's quickly talk about the midterm. So the midterm right now is scheduled to be on a Friday. I am actually, let me I want to think about it because I think last time I taught this class, I had a 2-hour class period for the midterm. So that I will double check on that and let you know, because we may shift it either to the Wednesday before, so March 13th, or the Wednesday after, so we have more time. So I'll get back to you on that. So the midterm is going to be in person. You have to come to your own campus in-person location. If you're not in Athens, you do not have to come to Athens. You can go again to your in-person campus location. These are going to be printed. It's going to be on paper, so you're not going to have to code, but there will be questions related both to coding and to precision ag. This course here, the intention of this course is to teach you how to use a programming language to run precision ag analysis. So there's going to be questions related to both sides of it. So for example, I may show you a map and then give you a partial code with some empty spaces and ask you to fill in the gaps or fill in the blank spaces and tell me, or the map you're looking at and the code you're looking at, what is needed in these blank spaces to make this map with this code? So that may be a type of question I will ask. I will definitely ask you questions related to SF. package in relation to the functions we've been using. So things that we're doing a lot that are really important. How to read, how to export, how to change the CRS, how to set a CRS, how are we doing that with these objects? So again, my goal here is not to ask you something that we never talked about. That's not my goal. My goal is to ask you things that we've been using a lot, and that I hope that you're getting across the point of why we do those things, and see if you're understanding. I will definitely ask you things about the papers you read. We're gonna be some questions related to that. There's gonna be questions about any lecture that we've had, could be question related to that. We didn't have too many lectures, but anyways, it could come from that. On the scripts, in some scripts, I do this more than others, but I also give you some explanation in the script as text. That is fair. It's fair for me to, it's fair game for asking questions about those comments that I make. And something that I want to, I guess, propose that you have this mindset, not just for the exam, but as you're learning through this class. I know a lot of times in class, we code and it may be too fast, and we may be more copying than really understanding. But I do want you to understand what we're doing and why we're doing these things, right? So let's say, and I think this semester I'm doing more of this with you all as far as asking, how would you do this? What do we need here? What function goes here? This is for me to check that you're actually thinking through, not just copying my code. I do want you to think through and be able to become, independent of me and be able to do this on your side when it comes to your own data. So, things like, I don't know, everything that we see here. So the question that Kumar had earlier, why do we have color equals to NA? This is not going to be a question because it's a very simple answer, but it's one of the types of things that I want you to be thinking about. Why are we doing this? Like, why am I changing this here? Because I try to make sure that we're changing the important things. And so you understand, the reason why. So a good way, let me come maybe to a chunk that has more pipes. Okay, this is a great one. So lots of pipes here, right? If you look at this code, even though we don't have comments here, I do still want you to be able to look at this and at least have some idea of what is happening in each one of these steps. So we're starting off with this data set, we're joining with the 19, we're joining them with the 20, then we're defining the row wise to calculate the mean SD and CV at the row level instead of the column. So I do want you to look at this and understand what is going on and what we're doing. If you go across, and this is just an example, this code is specifically not going to be part of the exam, but this is an example where a lot of times when we do the pipe, that helps with our code being more readable and avoid to creating a lot of in-between objects. But a lot of times our pipe flows may become very long. So if at any point you want to know so let's say if I wanted to know what is this function here doing? I don't know. And I want to at least try to understand on my side. What I would do is I go to the immediately previous pipe and I comment that off. And then I run the code until there. Because if I comment the pipe off, it breaks the flow here, it stops the flow here. So I run until here and I print my object, SYAll, and I look at it. Okay, it has X number of rows, X number of columns. This is what's going on. Now I let the pipe flow to the next function, but then stop the flow there. So then it goes through at least until here, and then I print it again. Okay, what is the difference? What happened between the previous step and this step? So that is a good way that you can try to learn what is going on in different steps of the pipe flow. Is just stopping the flow at a given point, running until there, printing the results, opening the flow, stopping the next pipe, and so on. So you comparatively can tell what's going on between each one of the steps. And again, I'm not going to be, the goal here is not to ask you something that we never talked about or never really discussed much, but there are some things that we're doing every single day. Those things I do expect you to know why we're doing, how we're doing, and so on. So those are fair game. All right, let me open up here for attendance. And just to let you all know, I have again, this program I'm part of this Friday, so we're not gonna have an in-person class on Friday. I will send you again, a video and code and resources for you to do this on your own. You can do this at home from your office. You don't have to come to the in-person location, but you do have to do it. As you're seeing, if you don't do it and then it comes after spring break and you don't have it, you're not gonna be able to follow. So make sure you do it, go through that, and then have a good spring break. Hope you can enjoy some time off, or at least catch up with anything you have. And yeah, I'll be in touch about Friday, and then let me know if anyone has any questions here or by email. We can touch base. Any questions online? Okay. I don't hear anything, so I think that's all. Make sure to claim your attendance, and I'll see you after spring break. Thanks, everyone.
Thank you.
Thank you.